Okay, so today we talk about projections and distances. We mentioned a little bit in the introductory lesson that we have the world, and the world is a sphere or almost a spherical shape, but people for a very, very long time have tried to put it on a flat surface. So they have tried to stretch it, to transform it somehow. And today we are going to learn a little bit about how this can be done. And I'm going to give some examples, even though there are very many out there. So if you're going to look for projections, and they are growing, people invent new ways of doing it all the time. And now I'm going to give just 3 examples and why people have been trying to do it in these ways. So the first one is called an azimuthal projection. These circles here that you see in red, they should actually be circles on the globe. So they are actually circles on the globe, but when you do the projection, they get distorted in this way. They have a name. If I remember right, they are called Tissot's indicatrix of transformation, which is a very, very fancy term. But anyway, you can see that the map doesn't really look right. It doesn't look like you would expect it to. There is some stretched behavior happening along the sides. But still, somebody has invented this projection, and it is useful sometimes. When exactly? It's useful for seismic activity. If you have an earthquake happening here, and this earthquake is going to make some kind of expanding activity, so it spreads, the circles in this kind of projection are going to be the same as circles on the Earth. So on the globe, circles here mean circles there. So it's one application. Then we have also something called a conical projection. It looks like this. You also see some stretching behavior here, but the circles just get larger as you go away from this starting point. They still remain circles. It will make some countries or some parts here look bigger than they should be, but the deformation is not one-sided like what we saw before. These are useful for flight navigation. These are useful for flight navigation, meaning that if you're going to draw here a line like this, saying that you want to go from that to that, this corresponds to the great circle distance on top of the planet. So if I measure this with my ruler now and multiply by the scale of the map, it's going to be equal to the length of that curve that you draw on the curved surface. So it has its applications also here, even though maybe you are not so familiar with this type of maps. I don't know. 2 years ago I had a student here whose father was a pilot. He almost was teaching this part of the lesson. Okay. The third one is cylindrical. And by the way, in each of these groups there can be multiple projections. Like you could have the cone wider or smaller, the cylinder bigger or smaller, this circle maybe bending a little bit. But those are the groups. So the cylindrical projection is something that you're most likely more familiar with, maybe from geography books, from atlases and whatever. This is actually called the equirectangular projection. It's when the cylinder has the same height as the diameter of the Earth. Even more familiar you should probably be with the Mercator projection. This is when the height of the cylinder is bigger, so then the points that are going to be, let's say here in the northern part of the Earth, in the equirectangular they follow those lines, but in this Mercator they actually go even higher on the cylinder than the corresponding location. And this makes the Mercator projection nicer in the sense that these circles remain circles even though they get stretched. So the equirectangular one has this stretching, this horizontal stretching more emphasized, but the vertical stretching doesn't occur. Okay, benefits of this one, well, it preserves directions, but it compromises the scale. And this is now something quite trendy nowadays on social media or whatever. People started to really talk and realize that this is a bad projection because, hey, this Greenland here cannot be bigger than Australia. It's somehow not. Like if you would look at it on a globe, then and measure the distances, Australia will look something like this relative to Greenland. So people are noticing these, and but still, for whatever reason, this projection is now default, and you can find it if you use Google Maps, Google Maps, OpenStreetMaps, any kind of maps as the default, even though they are able to switch if you try hard enough. So you can switch to different ones. I'm not exactly sure why this became so popular, but I think it looks decent. If you know that these the scaling happens, then it's an okay projection in my opinion. Okay. Any questions about these things? We will make a demo. We will write some code today, and I'm going to teach you this in reverse. Instead of teaching how to transform the Earth into a flat surface, I'm going to teach you how to wrap a flat surface over the Earth. It's called texturing in 3D graphics. So we're going to take the equirectangular projection, this one, and we're going to wrap it around the sphere, and we will see what the result looks like. So we will play a little bit with this and try to understand how the transformation may happen. But I'm going to group all the demos at the end of the lectures. Meanwhile, we can talk more about the round Earth. This is the equator. You probably know some of the things I'm going to tell you now, but I think some of them you probably don't know, so pay attention. Now this is another line parallel to equator, somewhere in the northern hemisphere, right? So this is the North Pole somewhere here, South Pole somewhere there. I say these are lines, but they are circles, really. I mean, if you remove the Earth from here, you would see the other side of the equator, and you would see it as a ring, as a circle around the Earth. And if you just walk around it in a straight line, you will come back to the same place. And you can go again and again and again and again. But that's the key thing here. It's if you go in a straight line, you will come back in the same place. Now the thing is, if you go in a straight line on this other line, you will not come back in, you will not follow this line. this is maybe a little bit counterintuitive, but this here is a straight line. You can follow it by just going without turning at all. But this one here, you must turn. It's easier to see if you look at the North Pole here. So if you look somewhere there, and this is your North Pole, this is my plot from last year. So if you're going to follow that line, you cannot go straight. You have to actually turn to go around. Of course, this actually happens for all of them. But closer to the equator, you have to turn less and less and less. There you have to turn more. But I think it's important to note this kind of thing. And here you have to turn in the other direction. Okay, so these are called latitude lines. So these are lines of latitude, what is going up and down parallel from the equator. Parallel concept on the sphere is very confusing, I think, because it doesn't really, I mean, we call them parallels, but by definition parallel means that they don't intersect. I can also say that this one here doesn't intersect with the equator, but I wouldn't call it a parallel. So I'm not very good at terminology here, but people don't usually use these kind of things unless you talk about flight patterns or whatever. But just keep in mind that it's not the most common thing that you are dealing with every day. This is a prime meridian. It's a line of longitude or longitude. People call it different ways. And it unites the poles. It unites the poles, and this point here is 0, 0. And there's nothing really there. It's like middle of ocean or something. But digitally, there are many things there. Digitally, this actually has a name. This is called Null Island. It's a place where all the geotagged information, all geotagged photos or whatever are displayed if something happens, an error happens, and the geotagged information doesn't go there. Null usually transfers into zeros. So if you're dealing with data sets, most likely you will have the biggest density of photos in the middle of the ocean there. And you may choose to filter them out if you're clustering it or whatever research you are doing. So just keep it in mind. So nothing there, but something is there. Then these other lines are a little different than the latitude lines because they all actually intersect in the poles. So this kind of looks like how you open an orange, the slices of an orange. These are straight lines, again, like the equator. You follow them in a straight line, you will be on that line until you come back to the same place again. Assuming you swim at the North Pole a bit. But yeah, so the radius of the Earth is about this much, 6,371 kilometers. This is a default value that people use. It changes slightly. It changes at the equator is a little bigger. I think it's about maybe 20 kilometers bigger, but if I don't know the value, you don't need to know the value. Of course, locally it can change, like Mount Everest is 9 kilometers or something like that. It's, yeah, come to think of it, it may be that Mount Everest is not really the tallest place on Earth if you count how tall it is relative to the center of the Earth. It could be something just here, even though it's not a mountain because of this 20 kilometer thing. Kind of interesting to wrap your mind about it, but I never really checked. But anyway. So this is Tuusniemi. It's city about halfway from Joensuu in Kuopio. So I'm using it now as an example here to favor both sides of this teaching. And it has coordinates. It has the latitude coordinate first. So in the northern hemisphere, 62.81. These latitude values, these are degrees. Okay, so they are degrees, how far up, what angle from the equator you go up, and how much from the prime meridian you go to the east. So that's what the latitude and longitude values mean. You can find them in different formats. Sometimes they have degrees and minutes and seconds and something like that. But here we won't deal with that format. We work just with floating point numbers because it's easier to work on the computer. The minutes, seconds can be in other contexts. But yeah. Now, if I would limit them to this much, it more or less it's going to be enough to represent Finland, maybe, or maybe even North Karelia, or these kind of regions in Finland. If you add a few more coordinates, a few more values after the decimal point, this maybe is enough for the city level. You would need to add a few more, maybe 2 or 3 if you want pinpoint accuracy, like as good as it can get. Like person doing his sports tracking, and you would get some kind of reliable statistics of how fast he's going. So you would need maybe 3 more decimals for that. Okay. They are called also WJS. Coordinates standing for World Geodetic System. You may hear this term in some places, WJS. And they are more or less alike, in a sense that we are living in a 3-dimensional world, right? So how can 2 coordinates tell us where we live, where we are? You always hear latitude and longitude, and you pinpoint accuracy where the building is or where something is. But the great assumption is that the radius is known, it's there, and it's a global variable. It doesn't change. You actually have the radius implied every time you hear somebody saying latitude is this, longitude is that. If you tell the ambulance, it's going to know where to come, even though you just gave 2 numbers, because it knew that the radius is implied. So just as an example, I'm here, but if I would be here, I would have exactly the same coordinates, latitude and longitude. And this applies for everything. This applies for International Space Station, flying somewhere in the space. If it just happens to be exactly on top of you, it will have exactly the same latitude and longitude. There are places on Earth where the sun can be directly on top of you. The sun will have the same latitude and longitude as yourself. So just the radius is different. So for all practical purposes, this is like a global variable, and it's assumed to be this much. And it works in practice. Okay. But now we start to do some math. And the question would be, what would be the x, y, and z values of Tuusniemi if we know the latitude, longitude, and the radius of the Earth? Well, we have this kind of parallelogram there. Okay? And first task is to figure out what is the value of this y. Okay, so what would be the y value if we know that this thing here is the radius? And we also know the angle. So the angle is this one. coming there, but don't peek. So how would we find it?
Pythagoras.
I'm sorry? Pythagoras. Well, Pythagoras tells you why if you know this one, but also this one. Now we actually know the angle and this one.
So it's a sine function.
Cosine.
Sine.
Sine
Sine or cosine?
Okay,
y over
maybe Kuopio side.
Sine, right?
y over hypotenuse is sine.
I'm sorry?
The value of y, if we know that, and we know that theta, and sine theta is equal to y by hypotenuse.
No, we don't know why. We
Y by hypotenuse.
y square.
Like that.
Yeah.
Yeah, okay, so then y from here
It's
comes
right, sine theta.
r times the sine. Okay, please write this down because I'm going to program it later and you're going to tell me what I should program. Yeah, so it turns out to be this value here. Yeah, sine, cosine, it can be a bit confusing, but sine means the opposite.
Catheter.
The opposite, I don't know if it has a name.
Catheter. I don't know.
Yeah, because the Pythagorean theorem is always enunciated in books in English like the length, the square of the hypotenuse is equal to the sum of the squares of the other two sides. And they don't have a name. I don't know how these other two sides are called in English.
But usually they are called like A and B.
Yeah, they are A and B, and you find out C.
In some languages
But,
they have some other names like.
Yeah, C is the hypotenuse. I know this is a fancy term if you want to use it. But the A and B, I don't know if they have a name in English or in Finnish. It would be interesting to enlarge my vocabulary. But okay, next. Since we have this y, could somebody tell me what is the value of this small r here?
Hypotenuse cos theta.
Yes, so it's the same but with the cosine there.
Yeah.
Yeah. Right. Okay. And it would have a value of this. Then I want to attract attention to this small circle on the top here that is forming that has a radius of small r, okay?
Mm-hmm.
So in this small circle that I'm seeing there from the top, we can find out now the x value, which is going to be the same as the x value on the big one, but I'm focusing on the small example here. So the x value is going to be, if we now know the small r, the angle here now, let's call it beta, is actually this one, so we know it. It's the longitude angle. So the value for x is going to be
Sine of beta.
sine of beta,
Beta times r.
the small r.
Yeah.
Yeah, we have two r's.
Yeah.
Have to be precise. Okay, so make notes of these because I'm going to need them. So that's going to be the value of x. And we're going to have a value of x programmatically. Wow, this looks horrible here. And finally a value for z, which is going to be
Cosine.
the cosine, yes. So you can see that these are quite simple things, but put together we can actually find, the location of Tuusniemi in a more familiar way if you consider what you learn in geometry during high school or whatever. We are in the 3D space, and this kind of coordinate system is possible. It's possible, and it's actually more intuitive than the other one, but it's not practical because you live on the Earth. So it's very unlikely that you need to deal with any coordinates inside the Earth or any coordinates in space. So the reason for the other one is practicality and 2 numbers instead of 3. And yeah, okay. And we will have a demo also where we implement this distance function. So this formula, the conversion from the WJS to this XYZ space. Now, if we know this XYZ value, of two places, we know now how to find it for Tuus near me, and we can do the same also for Dubai in this example. So my question is, what is the length? Oh, okay, sorry, it's coming. What is the length of this distance? What is this distance called? This is the Euclidean distance. It's a straight line between 2 points. How do I calculate this Euclidean distance between 2 points?
x2 minus
It's
x1
1 minus
Square root of
square root x2 minus x1
squared
square
plus
plus y z.
y. Yeah, the order of the subtraction doesn't really matter because of the square.
Very good. Yeah. So the order here doesn't really matter because the square root is going to balance things out.
Yeah.
But yeah, so this is the typical Euclidean distance. You can calculate it if you know it in this x, y, and z space. But in practice, it's going to be smaller always than this. So now we are going to learn to calculate this thing, which is more practical again. It's more practical because I'm not going to drill a hole between Joensuu and Dubai every time I want to go, even if it would mean sparing some kilometers, because it costs so much to drill the hole. Both of them have uses. Like if you're actually in space or something, you have satellites orbiting or whatever, and you want to calculate how long it takes to send a signal from one to the other, it's going to go in a straight line. Assuming space is not bending too much or whatever, but then there's nothing blocking it. And, yeah, too deep. We don't go there. But yeah, both of them have their uses. And also really important, if the points are really close to each other, it won't matter. Like the distance from me to you guys now, if I calculate using the Euclidean distance, it's going to be pretty much the same as using the Earth's curvature. Because the Earth's curvature changes so little that my floating point precision in the program is not big enough to notice any difference. To Kuopio, it may have a few meters, but not really a significant change. But to Dubai, or to the other side of the Earth, you can see that from this point here to the opposite point, it's quite a big difference than this one. So the bigger the distance between 2 points on the surface of the Earth, the more important for you is to actually learn to calculate this blue line. But for applications like finding the nearest restaurant, you wouldn't really need it. Okay, but how would we calculate this blue line now, which is called the Haver sign? So we have the Euclidean formula there. Now we're going to learn the Haver sign formula, or the great circle distance. Oh, I don't have anything helping me. I'm in trouble. Okay. I'm going to half this triangle, this big triangle, and also contact here. So my first purpose is going to be to find the angle, the big angle here. Let's call this alpha. And this part here on this 1/2 is going to be alpha divided by 2. But the reason why I'm halving this triangle is because I have here a square angle. So knowing this square angle here, I can use it for something. Now, the Euclidean distance here, let's call it E. We know how to calculate it. And this part here is also going to be E divided by 2. So I know it. I know the green line here because it's the radius.
Yeah.
Okay. So my question is, what is sine of alpha divided by 2?
Sine of x divided by 2.
Yeah,
E over 2.
I'm sorry?
E over 2.
So sine of this angle here. Yeah, I think you said E divided by 2
By R.
Multiply
By R.
by
R.
by
by
R.
R. Yeah, so E divided by 2 divided by R. Okay, how can I get rid of this sign here so that I get alpha divided by 2?
Sine minus 1. Sine power minus 1. No, I don't know.
Okay,
Alpha very small. Alpha close to 0.
I'm sorry?
If alpha is very small, we can write sin alpha by 2 as alpha by 2.
Yes, but I'm getting in your answer I'm looking for this inverse of the sine function. So the arc sine function. So if I'm going to do the inverse of the sine, I'm just going to get now alpha divided by 2. So this is equivalent to alpha divided by 2 is equal to arc sine
Of E.
of E by 2 divided by R. And if I want alpha, I have to multiply this by 2. Okay, so I have alpha. I have the value of alpha, this one, so this is alpha. And I just need to figure out how much is this blue line here now. So the next question is, how big is actually the circumference
Here.
of the Earth? So circumference of the Earth, let's call this
2 by R.
2 pi.
2 by R.
2 pi r, right? Okay. So this would mean the distance if you start in one point and go all the way around the Earth and come back to the one. But now you don't have to do that, you just have to go from P1 to P2, which is an angle of alpha. So this 2 pi r is actually going to be our max alpha, if you want to think about it like that. So we need to find out the ratio, how much is alpha out of the maximum of this, of
So
2 pi radians or 360 degrees.
we can switch alpha to radians and then compute the percentage or something.
Well,
R,
I'm sorry?
it would be R theta, where theta is the alpha by 2 pi. It's a radian angle rather than a degree angle.
Yeah, so it doesn't really matter what angles we use, but we will see that, I mean, what measure for the angle we use, degrees or radians. Formulas are more or less the same, but in programming it will matter because the functions that we call accept radians or accept degrees, so we need to be careful there. But yes, so here now we need to figure out this alpha. So if 360 degrees, let's maybe teach it like this,
Yeah.
means 2 pi r, then alpha means how much in distance? So this 2 pi r is a distance now, it's in kilometers. So our value is going to be alpha multiplied by the 2 pi r divided by the maximum angle 360 or 2 pi. It's the same thing if you use radians or something else. You're going to get your result in radians or you're going to get your result in degrees. So the measure is not important, it's just treating it well. Okay, So I hope you noted down all these things. Like how to calculate alpha, we have the formula here. And how to calculate this distance, so alpha multiplied by that divided by that, because you're going to help me in the second half of the lecture to actually implement this. So the demo 3 is going to have calculating distance between points. And demo 2 is going to be pinpointing tools near me or something on the Earth. So we're going to build something like a Google Earth application in HTML. But before I do that, I have to, we will have a break, but before the break, I have to attract attention to something. This thing. It's not the Mercator projection anymore. So for about a year now, Google decided to mess with my slides, and what is happening here is actually nothing new. It's they have done it before also. They have done it before also with the Google Earth application. It was prior to this, but in time the browsers became more powerful. WebGL, which is a port for the browser of OpenGL, became more accepted by other browsers, so they decided to switch it into a globe instead. So WebGL is able to display these 3D graphics, and we're going to use the same in our demo today. But what is this now? So what projection is it? I would say that this is something of an azimuthal projection of some sort. But the projection is constantly changing every time you are interacting with the globe. It has to be a projection. So the 3D model is somewhere, but it's being projected on my flat screen here. You can see very much deformities here, like very stretched things happening on the side. But because you have the power of bringing them into frame, and because you know that you have this ability to rotate thing, and you are expecting it to rotate, your mind somehow ignores this deformation. And you always have the power to bring into the center of the screen what you're interested in, and then the deformity disappears. Because it's as minimum as possible in the middle of the screen. So there are some advantages to this view, but see, until last year, it used to be like any other map service provider. Like for example, OpenStreetMap. So you just have the Mercator projection, and they have this kind of trick that it goes forever if you go to the right. But they changed it. So. Oh yeah, and they haven't changed it, if I'm not mistaken, yet on mobile. And I suspect that it's just using too much resources. So it is a little bit more costly to show the 3D thing instead of this 2D one. Okay, but we will have a 10 minutes break.